Now we are going to have the exponential the function as the sine cosine function. For example, I having here y equal to sine 2x. I can have here y equal to 3 sine 2x minus cosine 2x, or any combination of these. My yp will be equal to a sine 2x plus b cosine 2x. We will be having here y equal to 3 cosine 2x. So we're having the same yp. So we're looking at this, the coefficient of sine cosine is a constant. So if we're having here the function like this one, y equal to x sine x, are we having y equal to x cosine x, are we having y equal to 3x sine x minus 2x cosine x, any combination. So here we are having the coefficient is equal to the degree of polynomial 1. Now the yp will change, and yp will get here ax plus b sine, we're having a sine x, and then for this is coming for this polynomial degree 1, plus we are having here cx plus d cosine x. So that's the idea. Similarly, we're having the second degree polynomial again. We get here second degree polynomial here for this coefficient a, b, or a, b, c, d. These are the coefficient. We say undetermined coefficient, and we substitute in a differential equation and find the solution. We can have the case here. We are having the case 1. We are having the function f of x is combination of x plus 2 e to power 2x or e to power 3x. How we write yp? So we have two yp's. Here is our yp is yp1 and plus yp2. yp1 for the polynomial function and yp2 for the exponential function, and we say our yp is equal to yp1 plus yp2. So what's yp1? Is ax plus b, polynomial function of degree 1. What's yp2? This is a constant c e to power 3x. Case 2, we are having here f of x is equal to x square x e to power 2x plus here we are having sine 3x. So we are having here yp1 for x square, yp2 for this exponential function, 5p3, and our yp will be combination of linear combination of yp1 plus yp2 plus yp3, and we have just done before. So we write our yp is equal to, for x square we are having a x square plus bx plus c. This is my yp1 plus x e to power x, we are having here dx plus e to power 2x. Then we are having sine 3x coefficient is 1, so we get here this equal to, we will get here f sine 3x plus g cosine 3x. So this will be my combination for the yp. We have a linear combination of that one, and we can write like this one. Case 3, we are having taken here the addition y1, y2, y3, yp1, yp2, yp3. We have the multiplication. I have f of x equal to x square e to power 5x. We have done it before. We look on x square. We have only one y. We're having here this x square. We replace it by ax square plus bx plus c e to power 5x. So if I'm having here this case 1, this case 2, I am having here f of x equal to x square e to power 3x sine 2x. Now here e to power 3x sine 2x, the x will be giving us the information that we get here the coefficient as a polynomial function of degree 1. So my yp, here is yp, not f of x, yp. So my yp is equal to, for x we are having ax plus b, and this is coming with this one, we having e to power 3x sine 2x, then plus, because we have sine, so we get here sine and cosine, as we have sine and we have the cosine. If it's only sine or only cosine, we are having the combination. So we get plus cx plus d e to power 3x cosine 2x. This a B, C, and D are undetermined coefficients. And to find this undetermined coefficient, we substitute this one in given differential equation phi dy is equal to f of x, and we find the coefficient values of a, b, and c. I put the values of a, b, c, and d here, or a, b, c here. We'll get the particular solution, and our general solution, once we get the particular solution, don't forget our general solution will be the linear combination of the yc, the homogeneous part of the solution, and particular solution. If this f of x is 0, then yp is 0, our general solution will be only yc. So we'll give the examples and we'll show you how we can apply this idea which we are given in the last steps. So to apply it to find the general solution of non-homogeneous higher order differential equations. We're given a differential equation phi dy is equal to e to power 4 e to power 3x. We find first yc, and yc comes to be equal to, this is equal to e to power c1 e to power minus x plus c2 e to power 3x. Now when I want to find my yp, so I have here f of x given to me, that is equal to 4 e to power 3x. So my yp, as I discussed before, we get here this equal to, instead of the constant, we get here a e to power 3x. Now here the situation is different. When we write here y, then we have here already this value c2 e to power 3x and this a e to power 3x. So they are not linearly independent. So we can't write the linear combination of this one. So they must be linearly independent. So what we do, we say we multiply here by x. And multiply here by x, I modify my yp so that we're having not this one repeating, because this is repeating, so multiply by x. This is one example. I give you another example for this purpose, that we are having here, this is my example 1. Example 2, we are having here the differential equation whose yc is with me, this is equal to c1 cosine x plus c2 sine x. This is my f of x given to me is equal to f of x is sine x. So in principle, what I will get, my yp will be equal to a sine x plus b cosine x. But when I write my general solution, so my general solution of finding my a and b, then I can see it easily that this falls with this one and this falls with this one. They are not linearly independent. To make linearly independent, we multiply, because the roots are repeated, we multiply here by x, and that's the modification in the value of yp. Now we solve this one and we find our a and b, substitute our a and b here, that give me the yp. One more example, I'm having here my f of x is equal to e to power x 1 plus cosine x. This is my f of x, and my yc for the differential equation homogeneous part of my solution is c1 e to power x plus c2 e to power minus x. Now I want to write my yp. First I open this one, so I can write my f of x is equal to e to power x plus e to power x cosine x. Now we can see here they are repeating. They are repeating, then we can decide that my yp will be equal to, here I get a e to power x, and then get here this is equal to b e to power x cosine x plus c e to power x sine x. So this is my yp. But if I check this one, then I can see very easily that my f of x is repeating here. E to power x is repeating. So I modify this one and multiply this one with x. Now I substitute this in my differential equation. Phi d is equal to f of x, and find the arbitrary constants a, b, and c, and I can get the value of my yp.